If you work with language models, you know the drill. We take a word like strawberry, chop it up into a token, and assign it an ID. We do the same for strawberries. But in this process, the model loses a crucial piece of information, that these two words are almost identical. It has to learn from scratch that they are related, even though they share 9 letters. This is the pain of fixed tokenization. What if a model could see the raw text, understand the shared letters, and learn its own, more flexible representations? That's the core idea behind a new approach from Meta AI called the Autoregressive U-Net, or AU-Net. Instead of a rigid, predefined vocabulary, AU-Net processes information at multiple levels, creating what's called an adaptive multilevel hierarchy. Let's quickly refresh our understanding of tokenization before we dive into the significance of Meta's research. For language models to uncover patterns and predict what comes next, a crucial initial step is determining the individual components of a sequence, known as tokens. This is the core function of traditional tokenization. Traditionally, this choice is frozen in advance by a tokenizer that chops raw text into discrete units long before any training even begins. For instance, a character-level tokenizer would feed the model a stream of individual letters and spaces, such as T, H, E, E, Q, U, and ask it to predict the very next character, like I. In contrast, a word-level tokenizer would provide whole words, like the, quick, and expect the model to predict the next full word, brown, in one go. By far the most popular method is byte pair encoding. BPE works by repeatedly merging the most frequent byte sequences in the training text until a preset vocabulary limit is reached. This process involves splitting text once and building a static vocabulary. However, this traditional approach, while common, comes with several significant limitations, what we might call pain points. First, fixed granularity. Tokenization imposes a fixed granularity on the input text, which means the language model is stuck with that choice of how it operates on data and how far into the future it predicts. This locking in of a single level of granularity applies to all subsequent model layers. Next, opaque identifiers and lack of semantic understanding. Most issues stem from the embedding operation. Each token is typically mapped to an independent vector, meaning the network only sees opaque identifiers. The model has to rediscover, for instance, that strawberry and strawberries share 9 letters. This reliance on isolated embeddings hampers symbol-level reasoning. This rigid tokenization complicates transfer to different dialects or rare languages. Because the vocabulary is fixed, the model might struggle with words' forms it hasn't explicitly seen, even if they're morphologically similar to known words. The splitting process is most often a pre-processing step. This means the decision about how text is broken down is made before training, preventing any dynamic adjustment during the learning process. There's an inherent trade-off in the choice of granularity. Finer cuts, like character level, lead to larger sequences and shorten the look-ahead window for prediction. Coarser cuts, like word level or BPE with large tokens, lead to shorter sequences, but they make each token rarer and harder to compare and predict. Increasing the vocabulary size in methods like BPE allows for longer tokens and shorter sequences, but this comes at the cost of a larger embedding table and output softmax, which can be memory-intensive. This is where the adaptive multi-level hierarchy of Meta AI's Autoregressive U-Net, or AU-Net, comes into play. It's designed to overcome that rigidity. First, let's understand why it's adaptive. Instead of relying on a predefined, fixed vocabulary of tokens, AU-Net learns to embed its own tokens as it trains. This means the model isn't stuck with a preset choice of how the text is split up, offering much greater flexibility. By working directly with raw bytes, AU-Net completely avoids the need for predefined vocabularies and memory-heavy embedding tables, effectively allowing for an unlimited number of unique tokens. Imagine it can naturally see that strawberry and strawberries share 9 letters because it's processing the underlying characters, not just opaque IDs. This allows for a more flexible and less rigid way for a language model to operate on data. Now, for the multi-level hierarchy. AU-Net uses a clever architecture inspired by U-Nets to create a multi-scale representation of the text sequence. It does this in 2 main paths, a contracting path and an expanding path.
First, The contracting path, from fine to coarse.
This is where the model starts from the most granular view and progressively pools information into broader concepts. The model begins by processing the raw bytes of the text, much like character-level processing. This early stage allows it to handle fine details, such as spelling. Moving up, it then pools these bytes to keep only the vector at each word boundary. This is typically done by splitting on spaces using regular expressions, so it moves from individual letters to whole words like the, cat, sat. Further up the hierarchy, the model pools these words to keep one vector per two words. This allows it to look at broader semantic chunks, like the cat or sat on. In deeper versions of U-Net, it can even go a step further, grouping text into up to 4-word chunks. As the model goes deeper into these stages, it must predict further into the future, focusing on broader semantic patterns instead of just the next byte. Once the deepest stage of contraction is reached, the process reverses. The expanding path reconstructs the sequence by duplicating each coarse vector and applying position-specific linear layers. These upsampled representations are then mapped back to finer ones for the earlier stages. This allows the deeper stages to guide shallower stages at the semantic level, while the shallower stages continue to handle finer details like spelling. Crucially, the architecture includes skip connections between corresponding stages of the contracting and expanding paths. These connections are vital because they preserve fine-grained information that might otherwise be lost during the pooling process, ensuring that detailed context is retained across levels. Let's walk through a simple example. Imagine the input text is, "The cat sat on the mat." Stage 1. The model starts by reading the raw bytes. This is like character-level processing, where it sees every single letter and space, T, H, E, C, T, and so on. This allows it to handle fine details like spelling. Stage 2. Next, it pools these bytes into words. Using spaces as dividers, it now has representations for the, cat, sat, and mat. Stage 3. Moving up the hierarchy, it can pool these words into pairs. Now it's looking at broader semantic chunks like the cat and sat on. Stage 4. This can even go a step further, grouping text into 4-word chunks. The key here is that this process is adaptive. The rules for splitting the text can be defined by the user, and the model learns to embed its own tokens as it trains. This new approach has shown some significant benefits. It performs competitively with strong traditional baselines that use byte-pair encoding. It's much better at character-level tasks like spelling because it operates directly on bytes. It shows strong positive transfer to related languages. For instance, in tests, Germanic languages saw a 3-point gain on multilingual benchmarks, and Romance languages improved by about 4 points. This is because it can see the shared letters and word structures across these languages. And because it works with raw bytes, it effectively has an infinite vocabulary, eliminating the need for huge, memory-intensive embedding tables and the out-of-vocabulary problem. So, why the name? It breaks down into 2 parts. Autoregressive is a standard term in language modeling. It simply means the model predicts the next element in a sequence by looking at the elements that came before it. U-Net comes from its architecture, which is inspired by U-Net models used in medical imaging. It has a contracting path, where the sequence is compressed from raw bytes into higher-level chunks. At these deeper stages, the model anticipates multiple words ahead, letting it focus on broader semantic patterns. Then, it has an expanding path that reconstructs the sequence. Crucially, skip connections link these 2 paths. This allows high-level semantic information from the deep stages to blend with the fine-grained details from the early stages, like spelling. Of course, this is new research, and it has limitations. First, its current way of splitting text relies on spaces, so it doesn't work well for languages that don't use them, like Chinese. Second, while flexible, an engineer still needs to define the splitting rules for each stage. The model doesn't learn this automatically yet. Finally, there are some practical efficiency challenges with certain parallel computing setups, like FSDP, when using deeper hierarchies of 3 or 4 stages. So what does this mean for the future of LLMs? The U-Net approach opens up exciting possibilities. The most significant is the idea that tokenization now lives inside the model. Instead of a frozen pre-processing step, the model learns its own representations end to end. The immediate future work is to enable the model to learn its own splitting functions, which would overcome the current language limitations. This could lead to more unified models that can handle fine-grained character tasks and understand low-resource languages without needing separate specialized architectures. By seeing the real structure of words, like the relationship between strawberry and strawberries, it also paves the way for better symbol-level reasoning. This research marks a fundamental shift towards more flexible, adaptable, and integrated language models. So, what do you think? Could a future where language models truly understand the nuance of every word without rigid predefined tokens unlock a new era of AI communication? Let us know your thoughts in the comments below. Thank you so much for watching. If you found this dive into Meta's Autoregressive U-Net insightful and want to stay updated on the latest breakthroughs in AI research, be sure to like this video. Subscribe to our channel Returd and hit that notification bell so you don't miss our next deep dive.